my great pleasure to have my friend and colleague Merdad here from Surrey University. He's a full-time research associate now, if I understand right, with Rahim Tafazuli in Surrey University. We have been going through good times and tough times with the Femto project, but it's going pretty well. And he's essentially, his background is exactly what he's going to be talking about, the cross-layer scheduling. Well, I think there's an element of energy as well in there, so we will see what you will have to present today. So the floor is all yours.
Okay, can you hear me now? Okay, much better. Yeah. Great. So I think this presentation, maybe it was better if we had this presentation before the very nice presentation by Professor Barbarossa, because in this presentation it's gonna be like a prequel, so I'm gonna talk more about the basics and fundamentals of, I can say, resource allocation, and we're going to talk more about the optimization tools and what we can do to do the resource allocation, in particular for the case of femto cells. So in this talk, I'm going to start to talk about the cross-layer operations. What is the cross-layer operation, why we need that, and how it is done. And then we're going to focus on a specific subcategory of cross-layer optimization called air interface centric scheduling. Then we will going to see that where femtocells going to stand in this picture. And then we will talk about this scheduling as an optimization problem, and we also talk about the different notions and representation of optimization, and we also talk about fairness and other issues, and finally we talk about some specific challenges, and at the end I'm gonna conclude the day with concluding remarks. So first, I want to talk a little bit about cross-layer operation. Some people may be familiar with the notion, some maybe not. So, the three important questions are: what is cross-layer operation, why we need them, and how we do them. So, I think before we start to talk about what is cross-layer operation, I like to start with why we need cross-layer operation. So, basically, if we consider the Internet revolution in the past decade, this has revolutionized what we see as the traffic architecture. Now for the traffic architecture has evolved towards data communication rather than, traditional voice-based systems. And this requires managing the packets that are around in the network, and it essentially defines new elements in the system. First of all, to differentiate, the services at the packet level, and at the same time to be able to give priority to different entities in the network to access the resources of network. So in case of wired communication is more straightforward. This can happen by the definition of the quality of service at the packet level, as well as by introducing the packet scheduler across the different parts of the network. If we consider the problem in case of wireless network, I think it is more challenging, because wireless spectrum is a scarce resource, as we know, and achieving high spectral efficiency is quite crucial for wireless networks. At the same time, wireless spectrum is lossy, and it is more prone to, other losses like interference. And the many protocols right now that we have got in the in the internet, for example, like TCP, they have been originally designed for the wired systems. So these protocols are not fully optimized for wireless systems. Although the new variants are coming up, but still it is not something heterogeneous across all the network. So if we want to consider the packet scheduling in this type of systems, two issues are getting important. One is thinking about the channel status of the different users, or in other words, the channel profiles that we have got. And the other is the traffic requirements in terms of fairness or quality of service requirements of different users in the system. So if we consider all this and put it together, so we need a richer interlayer coupling in the system to support all these multi-objectives together and to be able to optimize our link and the total system together. So considering this, preliminary introduction, now if we want to talk about what is the cross-layer optimization, cross-layer optimization in general refers to any violation of layered architecture to adapt to the dynamics of the wireless system, considering service demand and channel profiles and issues related to them. So this cross-layer operation can be defined between different layers across the network, as you can see here in the picture. So what are the general trends in this cross-layer operation? In general, three major areas can be identified in this aspect that we have categorized them based on user-centric, root-centric, and air interface-centric. In the user-centric case, the most important factor is adaptation of important internet protocols to wireless channel to, in majority of cases, to achieve a certain end-to-end figure of merit, like end-to-end throughput or delay. And this is more focused on the upper layer of the protocol stack, like TCP. And here we have more abstraction for the channel modeling. So basically, less consideration is given to model all the contributing factors to the channel in majority of proposals. In the root-centric case, we try to incorporate the information that comes from different layers to find the optimal route across the network. So this type of cross-layer operation activities, they try to couple the network layer with physical, in particular with physical and MAC layer, to enhance the route selection process across the network. And the third and the main focus of our talk is going to be about the air interface-centric cross-layer operation, where we are more focused on the efficient utilization of resources. And for the efficiency here, we have got different measures, including the system throughput, fairness, and quality of service. So now we're going to focus more on this air interface-centric scheduling to see what is there in history and literature based on air interface-centric scheduling. So basically, if we want to talk about the scheduling, we should talk about the evolution that we had from the traditional concept to the current view that we have. In the traditional systems, we used to consider dedicated channels for different users across the systems. For example, this was actually valid for the cases like GSM systems. And in that period of time, we had the dominancy of voice traffic, and this system could be, sufficient for that period. But by moving, as I said, because of the evolution that we had in the data communication and moving towards more packet-centric systems, in the current view that we have a notion of shared channel, which has also been introduced in the new variants of, for example, UMTS systems like HSPA, and then from that point onwards to LTE and LTE advanced systems. So we have got this notion of shared channel, when we face this elasticity of the traffic, for example, for the case of internet, which gives us the privilege to prioritize our packets in the network based on the channel quality. And this will provide us this multi-user diversity gain. So in this new concept or current view that we have got this shared channel, scheduling and radio resource allocation plays a crucial part. So to better have a picture about this radio resource management dilemma, I can say, here I try to just talk about an analogic model, which we call it customer-provider model. In this analogic model, the mobile users that we have got across the networks can be seen as the consumers of goods, whereas the network operators are more similar to the providers of goods. So here we have got some, I can say, some contrast or some difference between the objectives of these two elements. Customers, they are more into bargain and quality goods, while providers are more interested in the net profit. So if we consider this generic picture here, where we're going to map that our resource allocation problem to this customer-provider model, what the first thing that we can see is the non-uniform distribution of cost across the systems. Of course, it is easier for a provider to provide goods at the local stores or at the places that are closer to the provider's stores. And this is basically due to less transportation costs that we're going to have. However, in practice, customers are not just distributed in the local stores. The customers are distributed in the entire area of network. So if the providers, they just want to simply focus on nearby areas, this will lead to losing far-off customers. So on the other hand, the far-off customers, supporting the far-off customers is quite expensive. So if we consider this generic picture, the provider's challenge would be to support goods for different stores at appropriate time. And therefore, in this situation, the low-cost seasons should be identified. So if we consider this picture, a scheduler would be the entity that is in charge of providing goods. And in different neighborhoods in the area, which is the customer possible location, as we mentioned, at the low transportation cost seasons, which reflects the better channel quality. There are other important factors that should be considered in this model. One is the balance in the provision of goods in different areas, which is a notion of fairness, and the other is the minimum expectations that user might have in the system, which is the quality of service. And another factor would be the coupling or some sort of competition that's going to be between different stores that can be modeled in the form of interference. So as you can see in this generic picture, the eventual efficiency of the system depends on multiple factors. So in this generic picture, where femtocells stand and what would be the position of femtocells in this generic picture. If you want to consider femtocells in this generic picture, femtocells would be like small shops that we're going to have in different neighborhoods. And of course, having these small shops would divide the transportation costs, and it would eventually provide us better opportunities to support different customers. And at the same time, it will help to increase the revenue for the providers in the system, because it will reduce the cost, and at the same time it will provide the opportunity to do better reuse of the resources. So the question that comes up is, what would be the catch in this scenario if we have many of these small shops? Of course, one issue would be about the maintaining these many small shops, which brings the scalability issue of the system. Another issue would be we need to prevent cannibalization of the traditional stores that we used to have when we are introducing these small shops. And at the same time, we should be careful to manage the feisty competition that might happen among small shops. So based on this, 3 solutions and 3 different aspects can be covered by regarding the maintaining, which we are moving toward more self-automation and self-organization. And at the same time, it is important to have a better control on interference in such scenario, both cross-tier interference between femto and macro, and also co-tier interference, which is defined between femto cells. So these are major issues that should be considered in this picture of radio resource allocation. So considering this model, now we can see the scheduling as an optimization problem. So generally, our objective is in this model, as we talked about it, if we want to see both customers and providers, demands and expectations, we need to have a overall system efficiency definition, which it can be modeled as an objective function. And this objective function would be subject to different constraints that comes into our problem based on the required quality of service, power requirement, interference requirement, and all different issues. So if we consider this model, the objective function can have different representation. It might have a cost minimization representation, or it might be as a profit maximization. So distinctive factor that comes between different models comes from how this cost or profit is modeled. So now we're going to talk about more about these optimization models. In general, if we consider the problem as the framework, in the framework of cost minimization, the most important cost that comes to the mind is the power that we're going to consume in the system. This is somehow analogical to the transportation cost that we talked about. So in this context, the problem can be defined as the minimization of total power in the system. In this formula, N represents the total number of users in the system, where Pn symbolizes the required power of user N. And this power comes from aggregation of the power that's going to be distributed over different resources in the system. As you can see here, the Kn has been used to show the fraction of resources that are eventually going to be allocated to user N in this optimization problem. Of course, considering this optimization problem, some additional constraints involved in this optimization problem. The first important constraint that we have got, which is specifically in case of intracell, is the exclusivity constraint, which implies the fact that each resource in intracell scale is going to be allocated to a single user. And this orthogonality brings some sort of simplification in the problem of resource allocation in intracell scale. And if we consider that this means that if a resource has been allocated to one of the users in intracell scale, of course, another user in intracell should not utilize the same resource. Besides this power, this constraint in intracell scale, we have got the another constraint which is more related to the quality of service requirement, or minimum rate constraint. So if we consider in this model, each user might have a minimum rate requirements, and this rate requirements here essentially tries to aggregate the achievable throughput of users on different resources, and then this minimum rate requirement can be theoretically different for different users in the system. Another constraint that should be taken into account is the target interference. So we might need to guarantee a minimum quality of service requirement for the primary users that we have got in the system, which are the macro users. So thresholds might be defined for the upper bound of interference that can be used or can be allowed from the secondary to the primary users. And at the same time, we might have similar minimum service requirements for the femtocells as well to guarantee a minimum level of service for the femtocells. So here these values represent the femto to macro, macro to femto, or femto to femto interference. So if we consider this cost-based formulation, as you can see, this cost-based formulation tries to find the optimal resource user pairs in the system in a way that it minimizes the total power consumption, and at the same time it tries to satisfy different requirements and constraints inside the system. And as it is obvious, this is an intercoupled problem between the resource allocation and power allocation in the system. And in generic form, and in the case that we consider the problem as a integer allocation of resources, this problem can be computationally complex. Later we come back to the solutions on how to tackle these kinds of problems. So after talking about the cost minimization, another form of representation would be profit maximization. The rate can be considered as the simplest form of profit that we can consider in the system. In this context, the problem can be formulated as maximizing the total rate in the system. And again, N here represents the total number of users, and again, Rn symbolizes the same potential aggregate rate of a user. And as you can see here, this eventual rate that the user is getting depends upon the achievable rate on different resources. And this is this depends upon the transmission power as well as the channel quality that we have got on this specific channel between the user and the base station. So similar constraints that we had in case of cost minimization, they are involved here, including the exclusivity constraint at intracell, and minimum rate constraint, as we talked about it, and also the target interference threshold constraint. Additionally, we have this total power constraint, as generally the base stations, they have got a limited amount of power that is allocated to them. So basically, the total power that's consumed in each base station or femtocell is going to be upper bounded by this consumption value. Still in this framework, we see this interdependency between the two problems of resource allocation and power allocation in the system. And in this form, it can bring significant computational cost. Another form of profit maximization would be in terms of utility. Utility functions are quite well known in the area of economics. The good thing about utility is utility can provide a strong coupling between the user level satisfaction and system level satisfaction, as it can be a subjective or objective indicator of user satisfaction. And normally utility is highly correlated with the achievable rate of a user on different resources. But this also, a utility function can embed notions of fairness and quality of service inside itself. So that's why it has more generic framework or representation compared to other cases that we have mentioned, to integrate everything inside one general objective. And of course, these formulations, as we talk about it later, are interchangeable and they can be transferred to each other based on the decomposition. So basically, as we see later, the shape of this utility is quite important factor in determining the fairness criteria or quality of service criteria in the resource allocation policy. So now that we have talked about utility functions, it is good that we talk a bit about fairness, because as I mentioned, in case of the utility functions, another issue that arises is regarding the fairness. and it can embed fairness inside it. So what is the notion of fairness? In general, in literature, if we look, the term fairness conveys different notions across the literature. Sometimes it refers to the rate fairness between the different users. Some other times it is based on the temporal or resource fairness. And it can also be imposed in short-term or in long-term perspective. So in case of, for example, if we consider rate fairness tries to bring some sort of balance between the rates that are allocated to the different users in the system. And in this sense, it looks similar to the minimum rate requirement or minimum quality of service requirement. But rate fairness can provide a stricter constraint on the allocation process, as it might not simply be satisfied by reaching that minimum rate or minimum quality of service threshold. And strict fairness policies can even have some sort of conflict with the main objective function that we have got in the system. So we should always consider the fact that supporting the poor users as far as others always going to have a higher price compared to the normal cases. So besides the rate fairness, we have got the resource fairness. When we talk about the resource fairness here, it is not important for us how the rates are allocated to different users, but we try to have some sort of balance in the provision of resources between the users. And these resources might be defined in time domain in case of temporal fairness, or it might be defined in frequency or code domain. And these are different notions of fairness. On the other hand, fairness can be imposed, as I mentioned, in short-term and long-term perspective. So considering the short-term fairness, this fairness is going to impose some constraints in a per slot manner or per snapshot manner, and this would be more stringent on satisfying the fairness criteria. So on the other hand, if we consider the long-term fairness is more relaxed and introduces a softer notion of constraint on our system, and it can provide a more degree of freedom to utilize the resources. For example, here we have got an example to show that imagine we have got a system that we're gonna monitor it in 2-slot time window. As you can see, if we want to apply the fairness criteria in the short-term perspective, in the first slot, we're going to allocate, for example, 3 resources to each user, and we're going to do the same thing in the second time slot. But as you can see, so this is a strict fairness criteria that we have applied. But as you can see in, for example, this scenario, as user 2 had a bad channel condition in one of the resources, anyway, it might not be able to fully utilize that resource, which has been shown in white. And similar case might happen for another user in another time slot. But if we wanted to apply similar fairness criteria in the time window of 2 slots together, as you can see, better utilization of resources was possible, whereas on average, we could have similar fairness criteria in long-term perspective. So talking about this long-term fairness, the notion of long-term utility comes up. So far we have talked about utility and profit maximization, but we have modeled this utility based on the instantaneous rate. However, in practical systems, in many cases, you see that this utility actually has been defined based on the long-term averaging value. And, for example, proportional fair, which is one of the famous schedulers, which is also used for benchmarking in LTE, HSPA, and other systems, is a more long-term utility function. And in this scenario, we try to define the utility optimization in a long-term perspective, and this is achievable through defining this real-time exponential averaging. As you can see, by using this real-time exponential averaging, still our utility is going to be a linear function of instantaneous rate that we have got. But this will give us a notion of long-term fairness, which is tunable through this alpha value, which is proportional which is inversely proportional to the time window that we have got for our scheduling problem. So now that we have talked about these different representations, in this part we're gonna more focus on the solutions to different representations that we have talked about so far. So in general, I can categorize the solutions in 3 different ways that have been seen in the literature. And of course, there are more and other heuristic ways to do to solve this problem. But 3 categories that I'm going to talk about it in this presentation are relaxation, splitting, and decomposition. Regarding the relaxation, as you've seen in this optimization problem, we have got an objective function and we have got some additive constraints, and these constraints impose some requirements on our objective function. So in case of relaxation, what happens is these prohibitive constraints are initially relaxed, and the relaxed problem can, in practice, can be more feasible to solve. And by relaxing that constraint, we can have a more feasible solution. And after that, we have relaxed the constraint and find the solution. We can reapply that relaxed constraints on the outcome or intermediate solution that we have got in this stage. Of course, by doing this approach, we might introduce some suboptimality because we are trying to initially solve a relaxed problem, but in many practical cases, the solution would be still near optimal. I'm going to talk about it a bit more in the next slide. Another approach that is in literature is based on the splitting. In case of splitting, we try to split the problem into simpler sub-problems, and then these outcome problems are going to be solved in a iterative or one-shot manner together. So essentially, we might have a master and a slave problem, or we might have equal problems that they interact with each other with some message passing. The other more systematical way of solving these kinds of problems would be through decomposition theory. Considering the decomposition theory, the constraints are integrated within the original problem, and the problem is decomposed in dual domain problem, and then we try to solve the dual counterpart of the original problem. I'll talk about this duality more in later slides. So regarding the relaxation, one important example that we have is regarding the exclusivity constraint. We have talked about the exclusivity constraint. As we mentioned, this constraint is usually applied in case of intracell scheduling, so resources are not practically shared between different users at intracell scale. So this orthogonality of allocation transforms the optimization problem to the domain of combinatorial domain, and in this case, finding the solution based on the exhaustive search can lead to a phenomenon called a combinatorial explosion, which is essentially exponential growth of the complexity with the growth of different variables inside the problem. So this is something that we want to avoid, and therefore this exclusivity constraint can be is a major tackle besides our main and original optimization problem. So one way that has been suggested in literature and has been introduced in many different frameworks is through time sharing. By using time sharing, we initially relax this exclusivity constraint, and we assume that users are allowed, are entitled to share resources in time between each other, and by doing so, the allocation variables, they transform from integer programming and binary programming domain into continuous domain, and better methods that are applicable to linear programming can be applied in this scenario. And then the solutions to this problem can have polynomial complexity, and which are more feasible. And then after that we have solved this relaxed problem based on the time sharing, then the relaxed constraints can be reimposed into our original problem and to outcome time sharing based solutions, for example, by a hard mapping to different users in the system. And in many practical cases, although this notion might be suboptimal, but near optimal performance can be achieved in many practical scenarios that are applied in resource allocation. Another notion that I talked about was splitting. In case of one way of splitting that we can talk about is, for example, in case of here, we consider a generic objective function which tries to maximize the objective function over the vector of x, which is our optimization variables. And as you can see, we have got some constraints beside the main problem, which tries to impose a minimum threshold to a function of our optimization variables. In scenarios like this, one way that has been heuristically used in the literature is we try to split the problem into double stages. In the first stage, we try to maximize the main objective function, ignoring the constraints that we have got in this problem. And at the next stage, we try to verify the validity of the constraints that we have violated. In case of the violation, for the resource allocation, we do some sort of reassignment. So basically, in this form of optimization, we initially go to the maximum achievable optimum point for our relaxed, unconstrained problem, and then gradually we are moving down from that point towards by applying the constraint in the system. Of course, by using such methods, it's really to guarantee the near optimality and convergence. Some conditions are quite crucial. First of all, we should consider minimum cost when we do this reassignment. So when we do the reassignment should happen ideally to the users that impose the minimal penalty to the system compared to the other users, which this brings us an intuitive figure of merit to do our ready resource allocation. And at the same time, the reassigned resources should be left out from the next iteration. Otherwise, the problem is not going to converge, and it may show some sort of oscillations in the provision of the results. And the algorithm should stop as soon as we have satisfied all the violated constraints. In this manner, we make sure that we have minimum distance from the optimal point of the unconstrained problem, and by this we somehow reassure the near optimality of the solution. Other more systematical way that we should consider for such problems and resource allocations is through decomposition theory. And here, as you can see, again, we have got a generic formulation where we want to minimize our objective function over our optimization variable set. And again, we have got some additional constraints besides the main objective. For example, this constraint can be the minimum rate constraint or whatever, if we think back in the original framework that we have talked about. So to use the Lagrangian duality property, initially we will relax all the constraints by using this Lagrangian duality theory. So this is how we form the Lagrangian, by introducing these new variables called Lagrangian multipliers, which are essentially the prices associated with each constraint. So by using this Lagrangian duality, we are introducing the constraints and the corresponding prices into a single closed form, which is the Lagrangian of the original problem, as you can see here. And this is somehow gives us the notion of dual objective, which is the dual objective would be a function of this new multipliers or Lagrangian prices. So this new function or dual objective is defined as the minimum value of the Lagrangian over the primal, I can say, optimization variables. And as you can see, as it's infimum over the original optimization variables, it would be a function of the dual variables. So why we did this? I mean, what's the good thing about this dual objective, and what nice properties we can get from this dual objective? In general, if we consider the characteristic of the dual objective as it is defined as the infimum of the Lagrangian over the primal variables, so we have got this specific condition which holds for any feasible set of primal variables and Lagrangian values which are essentially greater than 0. So this specific property tells us that we can get a lower bound on the optimal value of our primal objective, which was f, by simply maximizing our dual objective over its dual variable. So the difference between the values of these two objectives, which is primal and dual, at the optimal points, at the corresponding optimal points, is called the duality gap. So in general, based on the first characteristic that we talked about, this duality gap is going to be always a non-negative number, but it's not essentially 0. This is called weak duality in literature. So in general, then, as we said, this gives us just a lower bound on the main objective that we have got. However, if we consider the scenario where our primal objective is a convex function under some mild condition, it has been proven that this duality gap reduces to 0 at the optimal point. What we get from this is primal objective can be equivalently solved by dual at the optimal point, because they both, at a strong duality, give us the same value. So based on this, as we saw here, the important factor that gives us the capability to use this Lagrangian property and to use the dual decomposition theory is the convexity of the original objective that we have got here. So in this scenario, convexity is quite important. In general, we can say convexity is like the boundary between the easy and hard optimization. And because it provides us this strong duality condition, and by using this duality condition, we can essentially integrate our original problem and its constraints into the dual objective, and this will help a lot to decompose our problem and to find feasible solutions for our problem. So basically, if we want to mathematically define the convexity, a function like f is convex if for any sets of any variables like x and y in the f domain, all the linear combination of them would be in f domain, which essentially means that this function has a convex set as the domain. And at the same time, this condition should also hold for mathematically for a function to have a convex formulation. So if a problem is convex, then we could find the dual problem and we could solve our optimization problem through this dual. So the question is, now that we have integrated these constraints into this Lagrangian, how we can use this formula to solve our problem. So here we try to use a gradient or subgradient method, which is a efficient updating method to move gradually towards the optimal solution of this problem. As you can see, this is the formulation that we have got. So in case that the function that we have got, like g, is differentiable at the point lambda, then we can use the gradient method. But in case it is not differentiable, we're going to use the subgradient instead of gradient in this formula. And as you can see here, we have got an iterative update of all different Lagrangian multipliers. The good factor about this gradient or subgradient method is this would decouple our different optimal dual objective variables from each other, and it gives us the possibility for parallel updating at the same time to have a distributed representation of these pricing variables. And here, as you can see, we have got a step size, which is a positive step size, and this step size is quite important in using this gradient or subgradient method. Two factors are important actually in using this form of updating. One is the initial point that we start to update our gradient or subgradient, and the other is the step size that we move stage by stage towards our optimal solution. So generally, intuitively, this step size should be chosen as a small value, but it can be chosen as a fixed value in case that we want to have a totally distributed implementation of our algorithm. But at the same time, we can use, for more centralized solutions, we can use diminishing step sizes as well, which means that essentially by more and more iterations, our step size gets smaller and smaller. But of course, it should follow some specific patterns to guarantee the convergence and optimality of final solutions. So the important issue here is regarding the convergence to the optimal point and how fast we're going to converge to this optimal point. So far that we have talked, now we can use this convexity, because now we have talked about the convexity. So this convexity is quite important to see if we can use this framework to apply our problems. So it's important to see if the problem is convex or not. If we consider the radio resource allocation problem, for example, in case of femtocells, in low interference regime or in negligible interference cases, the problem gonna decompose across different cells in the system, and it has got this convexity characteristic. Therefore, the resource allocation and the power allocation is gonna be a per cell resource and power allocation. And power allocation, as already been discussed about it, is gonna have a water filling format. Here I've shown it based on the utility formulation, and as you can see, it's going to be utility-based water filling or multi-level water filling, which is dependent on the also on the marginal utility or the derivative of utility at the optimal point. And the resource allocation, as you can see, based on this formulation, is going to have correlation again with the marginal utility and the achievable rate that we have got on different resources in the system. So basically, in this case, we're going to have two problems of power allocation and resource allocation, and then we are going to have some iterations between these two problems to find the optimal solutions. But eventually, as you can see, we have got a mathematical closed form for both problems in case we are working in low interference regime. But in case that the strong or medium interference presence in the system, once the luxury of orthogonality is broken, the radio resource allocation problem is not convex anymore, and generally we cannot say that this dual strong duality holds, which means that the gap between our primal and dual solutions is not necessarily non-zero. However, in the case of multi-carrier systems, it has been proven that under some specific conditions, still, although the problem is not convex, this duality gap reaches zero. And this has been proven to be valid for the case of the systems that they have got very large number of subcarriers, or in theory it should be infinite number of subcarriers. But as in OFDM systems we have got a huge number of subcarriers, this strong duality can still give us a really good approximation in case of OFDM systems in a specific, and this opens up, of course, the possibility of solving the problem again by using the dual, the problem in the dual domain. Although this is possible, but because of the interdependency that this coupling factor, which is interference, brings between different equations, this time, I mean, the optimization would not be as straightforward as the case that we have low interference. And this interdependency brings us significant amount of complexity because of the nested iterations that are required, and some variants of iterative water filling solutions has been proposed in literature for this case, although the optimality of those solutions are not proven, and those solutions are going to be suboptimal solutions with a more limited amount of complexity. However, recently in literature, for the notion of dense femtocells, we have got a new achievement. In this scenario, based on the investigation that has been done, if we consider the iterative water filling solutions that has been talked about it in the previous slide, these iterative water filling solutions, they provide some specific properties, specifically in case of dense femtocells, and to see how dense condition would hold based on the investigation that has been done, scenarios with where femtocells are located with a maximum distance of at most 70 meters from each other, and even up to 8 femtocells can be still considered dense, which is a good start for practical scenarios, for example, which is more or less in line with, for example, practical models that is being used, for example, in industrial systems like LTE, like 5x5 grid. So in this situation, this typical form, what's the characteristic of this form of solutions? It has been shown that this type of iterative water fillings gives us a specific form of solutions where only one base station loads power on some resources, whereas other base stations load negligible power on those resources in dense scenarios. This gives us a really nice binary power allocation property, meaning that, for example, at each time, in case of dense systems, one base station with better channel condition is going to load that subcarrier, whereas the other base stations should back off from transmitting on that specific. Yeah.
Isn't this a classical property we have in information theory? We already know that in high in interference limited scenarios, you consider an interference channel, which is basically what you're considering.
Yeah.
So the optimal solution for at least the sum rate maximization is the one in which you allow only one of the transmitters to transmit, and you have to turn off all the users,
Yeah,
all
exactly.
the other base stations. So
That's
this is exactly what, right?
Yeah, that's a good point. But that case has been proven for the case of single cell scenarios when we do not consider interference.
No, it is basically interference channel when you have multiple cells. So each base station is serving one user, and that is a classical interference channel scenario. You try to maximize the sum rate. The optimal solution for that in an interference limited scenario is the one in which you just turn on one base station, which is exactly what you are doing. So this is a classical information theory.
In case of femto cells, I think this problem has been recently identified, but I don't know. Maybe because I think this interference condition, saying a strong interference, is really dependent on the scenario. Because in case of femto cells, to identify this strong interference is quite important. As it's been found recently in the literature, this case is valid for, because in case of macro cells, we could not, I think, generally say that this would be a valid case in many macro cell scenarios. For example, because macro cells, the users that are deployed in case of macro cells can have different values of interference. But I think in this specific form of femto cells, which gives us the dense scenario, this is more feasible.
All right.
Yeah.
Thank you.
So based on this, it's been shown that based on this scenario, allocating the power optimally based on this binary power allocation can be more rewarding than different variants of IWF, which is iterative water filling solutions. And basically, the systems that modeled based on the capacity of the systems that are modeled based on this optimal binary power allocation can give us a higher capacity compared to different variants of IWF solutions that are in the literature. But there is an important condition, which is this dense condition. I mean, if you want the mathematical formulation, you can go to the references that I've got at the end of the presentation. So, but this dense condition has been numerically proven can hold in many practical scenarios of femto cells. For example, specifically, for the case of 5x5, when they consider in the LTE deployment, they have got a 50 meter by 50 meter deployment of the femto cells, and each block is 10 meter by 10 meter in this 25 blocks inside the grid. So this scenario matches well with such deployments. So considering this binary power allocation, if the power is allocated in binary fashion, of course the resource allocation problem is significantly simplified and the complexity reduces to polynomial level. And in this mode, the resource allocation is more simplified, as we want to find the best base station to transmit per resource, and at the same time, we want to select the best receiver on each resource. So this interdependency between the problems decoupled in this scenario by considering this binary power allocation. So based on these different factors that we have talked about, so important challenges that can be seen in this optimization framework that I talked about. First of all, we should note that decomposing a problem does not have a single solution, so we can decompose the problems in different cases based on different scenarios, and it depends on how and what variables are used in the decomposition. And each decomposition going to have a different practical realization for either case of femto cells and macro cells. And of course, for the case of femto cells, as we are looking for scalability and feasibility or more distributed solutions, some notions of decomposition might better fit in case of femto cells compared to the case of macro cells. Another issue is in case of decomposition is regarding the complexity. As we talked about it, generally these solutions are iterative, so they require passing some pricing messages between different entities in the network. So ideally, we like the algorithm to converge faster and to guarantee the convergence of the algorithm. So having faster convergence for the proposed algorithm is another important issue that needs to be considered. And of course, as we need to pass all these messages across the different entities in the network, the reduction in the size of pricing variables in some forms of decomposition is also an important issue. And as we talked about it regarding the way we choose the initial point and also the step size, it gives us, it actually shows our location inside the search space. So as if we have more and more limited spaces, so this would give us faster solutions and possibility of faster convergence in the algorithms. Regarding the efficiency, as we talked about it, some solutions are not totally optimal. So it is really important that when we come up with heuristic algorithms to see how far away are we from the boundary of capacity region. So the closer we are to the boundary of this capacity region, our solutions are more efficient. And of course, in this scenario, it is important that to come up with more tunable measures to be able to just target any locations in this boundary of the capacity region. In many scenarios, using this gradient or subgradient method might have a stability issue because the optimization parameters, whether in primal or dual domain, they might be quite sensitive to the changes that we apply to the optimization variables by gradient method. So it's quite important that we make sure the stability of the system. Yeah.
One question to the previous slide.
This one?
Yeah. You say choosing best base station and selecting best user. Where exactly is the simplification here? Because I mean, you don't decouple the problem. I mean.
No, the thing was in the original problem, the factor was different base stations could transmit simultaneously on different resources. So that power factor, that would brought this uncoupling factor. So in this manner, this problem has been decoupled, so it's easier to just update it in the resource allocation domain. And so yeah, so these three different issues are quite important regarding the efficiency of the system, especially in different femtocell scenarios. So basically that was my talk about this. As the concluding remark, we talked about this cross-layer optimization, about the necessity and definition and the general trends that we have got there. And then we are focused on a specific form of cross-layer operations that we termed as air interface centric scheduling. And we try to understand it better by customer-provider model. We try to see what's the position of femtocells in this model, and we try to see scheduling as the optimization problem. We've talked about different methods of representation. We've talked about the fairness issue, utility optimization, and we have also talked about different ways of optimization based on heuristic solutions or based on near optimal solutions. And we have also talked about some challenges that might come up in using such optimization tools and optimization scenarios. So thank you very much for listening to this presentation. And this is the list of references if you want to have a look at them in more details. And that's it. Thank you very much.
Okay, thank you, Mehrdad. If any questions, please. Good. Okay, so in case if there are no questions, let's thank again Mehrdad for a nice presentation. Okay. And this is the end of today's session. And tomorrow we'll start on self-organization with Misha's talk. And as he told, we'll end on Misha's talk as well. And I'll be sandwiched in between. So tomorrow is the revenge day for you. Okay. So thank you very much. Okay, then see you. Bye.